All right. Well, today we're going to talk about nuclear weapons, apparently, and exponential growth and decay. We're going to look at exponential growth and decay, which is based on a single equation. It seems like it's a very useless thing to do to spend a whole hour on one equation, but it's actually an equation which governs lots and lots of different kinds of systems, things that change over time. Okay? So exponential growth and decay can be used to model lots and lots of different things, which is why it's such an important concept. Okay. So I want to talk about something called a differential equation. But first, let's remind ourselves what we did last time. We looked at the derivatives of logarithmic and exponential functions. That is e to the x, natural log of x, a to the x, where a is a number different from e, and log base a of x. Okay, so we did those 4 derivatives, and we looked at problems involving also logarithmic differentiation, a very cool technique for finding derivatives of functions that are defined using products and quotients and powers without using the product rule, the quotient rule, and the power rule. Okay, but now I want to talk about something called a differential equation, and that's a new term we haven't really talked about that much. Our department teaches an entire course on differential equations. Actually, we teach 2 courses, ordinary differential equations and extraordinary differential equations. No. Ordinary and partial differential equations. And so there's lots you can do. There's lots of current research going on in differential equations. So we're really only scratching the surface. The basic idea is that a differential equation is an equation where the unknown thing is a function. Most of the time we think about equations as a statement about a number, like x squared minus x plus 3 equals 0. That's an equation for an unknown x. But a differential equation is an equation for an unknown function, and the information that's given in the equation involves the function and its derivatives. Okay? Now, most of the time, we're thinking about things that change over time, and those are the functions that are solutions to differential equations. So we are commonly used to saying the independent variable is called x, but because so many of our functions are functions over time, we'll let the independent variable be t. Okay, so a very interesting example of a differential equation is Newton's second law, F equals ma. Okay, a is acceleration, and we know that acceleration is the derivative of velocity, and velocity is the derivative of position. So if the position of some particle is given by a function x of t, and the force that the particle feels is given by a function f of x, then this represents a differential equation for the motion of the particle. Okay? And this is actually how Newton expressed these laws when he wrote Principia and described the laws of nature through mathematics. Here's an example of a differential equation for the motion of a particle. If you have a spring or a rubber band, I guess the rubber band is the opposite of the spring. But if you stretch a rubber band, then there's a force that's pulling it back together. And the further you stretch it, the greater the force that pulls it back together. And Hooke's law is the law which describes the force in a spring. It says that the restorative force is in the opposite direction and proportional to the displacement from equilibrium. Okay, so if you stretch it out a lot, x is large, then the restorative force is large in the opposite direction, in the restoring direction. So if this is your force equation, and this is your acceleration, then you have an equation for the unknown function x of t, the position of the rubber band at time t, which looks like this. Minus constant times x of t equals constant times x double prime of t. That m is just some kind of weight of the spring. Okay, you can play around with that and write it in this sort of standard form, x double prime of t plus a constant k divided by m, x of t equals 0. Okay? Looks like a very complicated equation. To simplify things, let's think about, say, this constant here, k divided by m. What if that were just 1? Then we're looking for a function whose second derivative is the opposite of that function. The second derivative of x of t is the opposite of x of t, negative x of t. Do you know of a function that satisfies that property? Its second derivative is the opposite of itself. Sine. Sine's a function which works like that, because you take the derivative of sine, you get cosine. You take the derivative of cosine, you get negative sine. That's the opposite of sine. Anything else? Is that the only function that has that property? Well, let's see. It turns out that any sine plus any cosine will also have that property that the second derivative is the opposite. Okay? Maybe not exactly the opposite, but if it's the sine of some frequency omega times t, then its second derivative will be, let's see, negative omega squared sine of omega t. So negative constant times sine. And so this is the exact kind of equation which satisfies, exact kind of function which satisfies a differential equation like this. Okay? So solving differential equations is actually kind of complicated, but checking that a function satisfies a differential equation is actually easy. If you take this function here, x of t equals a sine omega t plus b cosine omega t, take its first derivative, well, the omega comes out by the chain rule, a omega cosine omega t. The omega here comes out by the chain rule, negative b omega sine omega t. Do it again, you get another omega and another omega. Cosine becomes negative sine, sine becomes cosine, and I have negative a omega squared sine omega t minus b omega squared cosine omega t. And that's omega squared times the opposite of x of t. And that's exactly what we would have. Okay? Now, like I said, we have entire courses on differential equations, and this would be an equation that we would study in a course like that. We're going to look at some much more simpler equations, such as the equation y prime of t equals 2. So who can tell me a function y of t whose derivative is 2? Anyone? 2x, okay. Remember we said we're going to let the independent variable be t. And that's why I wrote y prime of t. So instead of 2x, we would say 2t. There you go. Okay. Now, there are lots of other functions whose derivative is 2t. Can you name another one? What's another function whose derivative is, another function whose derivative is 2? Yeah? 2t plus 1. Okay, anything else? 2t plus 2, maybe? 2t minus 1? 2t plus anything is a general solution to this differential equation. So what we find in the world of differential equations is that if you just have an equation, there is often some parameter that comes in. In this case, there's a constant we can add. All right? So one solution would be 2t. All of the solutions look like 2t plus constant. If you're solving a differential equation, oftentimes you'll get one piece of information about the function. So you might say it satisfies this differential equation, but also y of 0 equals 1. And that initial value allows you to find out exactly what constant would have to be taken. Okay. So the upshot here is that if you have a function that grows at a constant rate, right, that grows at a constant rate, in this case it's 2, then that function is a linear function. Right? You know that, if the slope is constant, the function is linear. Okay. How about y prime equals 2t? Find a solution and then find all the solutions to this differential equation. Yeah? T squared. And where did you get that? Oh, okay. So you reverse the derivative. He's smart, and he knows that the function t squared has as its derivative 2t. So, right? And that's not too hard to check. Just take the derivative. And so the most general solution to the equation, what do you think? T squared plus c. So one solution would be t squared. The general solution would be t squared plus constant, because taking the derivative of this constant gives me 0. So far, so good? Man, differential equations are easy. How about this one? Y prime equals y. Yeah. E to the t plus c. Okay. You jumped all the way to the end. So where does e to the t plus c come from? Mm-hmm. Okay, so the derivative of e to the t is e to the t. We spent a whole day on derivatives of exponential functions, and that was what we said was special about the function e to the t. Well, we called it e to the x, but e to the t has as its derivative itself. All right, so that means y prime equals y. Now, we could alter that by a constant. So if I take the derivative of e to the t plus c, do I get e to the t plus c? I take the derivative of e to the t plus c. What do I get? I get e to the t. Okay, so if y is e to the t plus c, the derivative is not exactly y. It's y minus a constant. So I would agree with this one that one solution would be e to the t. But in this case, the general solution is not constant plus e to the t. Because if I add a constant, then its derivative doesn't have that constant added on. So what's different this time? Multiplied? Okay. Why multiply? Well, if we multiply e to the t by a constant, then take its derivative. The constant multiple rule says that the derivative of this constant multiple is that constant multiplied by the derivative. So the derivative of c times e to the t is c times the derivative of e to the t. The derivative of e to the t is e to the t. And so I do get the exact same function. Okay? Adding the constant doesn't work this time. In this case, we have to multiply by some constant. Okay? And the difference is really the difference between an equation that has y prime and y in it and an equation that has y prime and t in it. When the equation looks like this, this is called homogeneous. And what's the other word? Autonomous. Then the constants are often multiplicative like this. Okay? So that's an important distinction between the other equations that we've been looking at and this one. Now, what about that constant? Well, we'll find out that the constant actually can be used can be interpreted from the system itself. Okay, but before we do that, let's think about improving our class of differential equations that we can solve. Y prime equals 2 times y. So first, find a function whose derivative is twice itself. A function whose derivative is twice itself. Okay? Thinking about exponentials, we know that the derivative of e to the t is e to the t. But we also know that if you have an exponential to a function, then its derivative needs to be multiplied by the derivative of that function. Okay, so what would cause the derivative of a function to be a multiple of that function, a constant multiplied by the function? Any ideas? 2y? Well, you need to tell me what y is in terms of t, right? You can't say 2t. Just y equals 2t? Oh, okay, y equals 2t times e to the t. But then we're going to need the product rule. It doesn't sound like it's going to work out, right? But multiplying the function by something is a useful technique. Any ideas? How can we alter e to the t? Yeah? 1/2 y. Well, see, the problem is that we have to give our answer in terms of t all by itself. Our answer can't involve y. Right? I say, what's the function y? You can't say it's y. You have to say it's something of t. You got it? E to the 2t. How about that? If you take the derivative of e to the 2t, then you get e to the 2t times the derivative of 2t, which happens to be 2. And that's exactly what we want. Okay? Yeah? Question? Should it be 1/2 times e to the 2t? Yeah. If the function were 1/2 e to the 2t, then the derivative would bring out a 2, which would cancel the 1/2, and then you would get e to the 2t. So that would be a function whose derivative is itself. But so is this. Right? And any function, any multiple of e to the 2t, whether it's 1 times e to the 2t, or 1/2 times e to the 2t, or 77 times e to the 2t, those would all be solutions to that equation. Okay? Now, what if we replace 2 by some general constant k? Can you think how the solution to this differential equation, y prime equals ky, would change? What do you think? What do you think? Go ahead. this. C times e to the kt. I jumped the gun. Sorry. I thought you were going to say it just a tiny bit faster, but there you go. Right, the derivative of constant times e to the kt is that constant times e to the kt times k, because the k is going to come out from the chain rule, and that's exactly what we want. Now, what about that constant? If you plug in t equals 0, what you get is that y at 0 is equal to that constant, c, whatever it is, e to the k times 0, but that's e to the 0, which is 1. So the constant c turns out to be the initial value of y. So the c is not just a random parameter in the solution to the differential equation. It's actually an important part to the system that you're analyzing here. It's the initial value. So sometimes we'll call it y sub 0, the value of y at time 0. Okay? This k here is not an arbitrary constant. That k is really going to depend on the system you're analyzing. So you've got some thing you're modeling, and you'll say that it satisfies some differential equation, and that differential equation will have this thing k in it. But the solution has a parameter c in it, and that's something that you'll have to come up with when you solve the equation. Okay? So general result is that any time you have a function that has a constant relative growth rate, then it has an exponential solution. Okay? Constant growth rate means linear solution. Constant relative growth rate, that is, y prime divided by y is a constant, then the equation is going to have an exponential solution. Okay? And the general form of that solution will be some constant, which is usually y of 0, times e to the kt. Okay? So that's the basic idea. What we're going to look at is different problems that can be modeled using constant relative growth rate laws like that. Okay, so questions about the solutions to these equations so far? That's as much generality as we're going to get into with differential equations. Okay, let's look at some specifics then. Well, like I said on Monday, there are lots of situations where we witness exponential growth and decay because there are lots of places where you have these constant relative growth rate laws. Like asexual reproduction, we've got this culture of bacteria, the number of child bacteria which are produced is proportional to the number of bacteria that you actually have. If you have a lot of bacteria, you have a lot of new bacteria. If you don't have that many, well, then there's not that many which are going to be reproducing, and so you don't have that many new ones. If you don't have any at all, well, obviously you won't get any new ones because you can't create bacteria out of nothing. Money in a bank account also has this behavior because if you are collecting compound interest, then the amount of interest that you get is proportional to the balance in the bank account to begin with. And then social networks can also grow in this fashion because as you start in the center, you add a few of your friends, and then you get exposed to their friends, and so your circle widens. There was a time that my friend list was growing exponentially, but that's when I was playing Mafia Wars. I'm finished with that, so now my friend list is stabilized. Anyone need 500 pairs of night vision goggles? Okay, so let's look at a few examples where exponential growth and decay are found in science. Okay, so we talked a little bit about this already. Now we're ready to formalize our approach to asexual reproduction. So the way that bacteria and other single-celled organisms reproduce is that they just divide, right? They just go, and they just pop off another copy of themselves, and suddenly you have a new organism. So what that means is that the number of new organisms you have in any culture is proportional to the amount of adult organisms that you have. Because at any moment, any of them could be reproducing. And so that means we have a constant relative growth rate law. Bacteria populations will grow exponentially. So let's look at an example where we could apply the exponential growth law to solve an equation. A colony of bacteria is grown under ideal conditions in a laboratory. At the end of 3 hours, there are 10,000 bacteria. At the end of 5 hours, there are 40,000 bacteria. But unfortunately, we forgot to count how many there were to start with. So can we use this information that there were 10,000 bacteria at 3 hours, 40,000 bacteria at 5 hours, to find out how many we started with? Okay. Everyone understand the problem? We have two data points on the growth curve of this culture population. And what we want to know is another one, right? So we have to fit it to the right exponential curve and then backtrack to time 0. Whoops, sorry. Okay. So because bacteria obey this constant relative growth rate law, the evolution is going to be exponential. So we have to fit it to a curve y equals y0, initial y, e to the kt. The two things that we know are that are two different values of the population. And they are 10,000 when time is 3, and 40,000 when time is 5. So what don't I know? I don't know k, and I don't know y0. The thing I'm actually asked to find is y0. So I have these two equations that I need to solve for the two unknown quantities, y0 and k. All right. That's the plan. We have to solve these equations. Now, how do we solve these equations? If you have two equations with two unknown things, unless you were unlucky and one equation is really just like a multiple of the other, then you can always solve these and get your unique unknowns. Okay, but how do you solve equations where the unknown is in an exponential? Okay, it's a little bit more complicated than just two linear equations in two unknown things. Well, let me show you a technique for solving equations like this. One thing you can do is take one of the equations and divide it into the other equation. So if I take that the second equation here, 40,000 equals y naught e to the k times 5, divided by the first equation, 10,000 equals y naught e to the k times 3, then it looks like this. 40,000 divided by 10,000 equals y naught e to the 5k divided by y naught e to the 3k. Now the 40,000 and the 10,000 cancel to give me 4. The y naughts cancel completely. E to the 5k divided by e to the 3k is e to the 2k. So dividing the two equations isolated one of the unknowns in its own equation. So I've got e to the 2k equals 4. Now that's actually an easy equation to solve because we know the function which inverts exponentiation, the inverse function to the exponential function, is the natural log. So the natural log of 4 is the natural log of e to the 2k, and the natural log of e to the 2k is 2k. That's what ln does. It undoes the effects of exponentiation. Okay, so we've got natural log of 4 is 2k, and so k is the natural log of 4 divided by 2. Now you can simplify the natural log of 4 because 4 is 2 squared. So the natural log of 4 is 2 times the natural log of 2. We're dividing that by 2. We end up with natural log of 2. All right, so we have discovered that the growth parameter k is natural log of 2. Make sense? Okay. A little bit complicated to solve an equation with unknown things in the exponent, but this technique of dividing equations sometimes helps. And then once you've got a single equation with the unknown in the exponent, then you just take the natural log to get it out of there. Okay, so that was k. Did we want to find k? Actually, we were not asked to find k. We were asked to find y0. But now that we have k, we can plug it in because we know that the equation looks like y0 e to the t times the natural log of 2. Take that and plug in one of the points you already know. For instance, at time 3, we have 10,000 equals y naught e to the 3 times natural log of 2. And that's what we want to solve for y0. Now, again, using properties of exponentials, e to the ln2, exponentiation and logarithmic and natural log cancel each other out. So e to the ln2 is 2. 2 to the 3 is 8. And my equation looks like y naught equals, 10,000 equals y naught e to the 3 times natural log of 2, which is equal to, there's a typo here. There should be a y0 here. 8 times y0. Divide that equation by 8, and I get y0 equals 10,000 divided by 8, which is otherwise known as 1,250. I want to make sure I correct that before I put it online. Oh, okay. So any questions about this problem? The exponential growth law gave us two equations and the two unknowns, and then we just had to solve it. Okay. So let's look at another application of this kind of growth law, and it's called radioactive decay. So I'm not a biologist, and so I sort of faked my way through the asexual reproduction thing. I'm also not a nuclear physicist, so I'm going to fake my way through this process of radioactive decay. So the thing is that in a nucleus, you have a lot of forces acting in contraposition to each other. You've got the electromagnetic force, which pushes apart things of the same charge, and you've got the strong nuclear force, which pulls together the nucleus of the atom. The strong nuclear force is much stronger than the electromagnetic force, but if you have a large nucleus with a lot of positively charged particles in it, then they're going to be pushing each other apart at the same amount that they're pulling each other together. So when that happens, you've got this nucleus which just sort of like is agitated by these forces in opposition to each other, and it will just go, ah, and blow off either some energy or some matter or both. The nucleus splits into two smaller nuclei, and so that larger element becomes two atoms of smaller elements. Okay, and what's really interesting is when you've got other nuclei in the neighborhood, so that if a particle like this runs into another nucleus, it might force it to break apart, and then the other one will break apart and break apart two more, and this is how nuclear weapons are made. You've got these nuclei which are splitting each other, and it just releases massive amounts of energy. Okay? And this is a process which you can't really measure or predict. We know that it happens. We can't say when it happens. But we know that if we have any radioactive particle, at any moment, there's a certain probability that it will decay into two smaller things. Okay? So if you have a measure of radioactive substance, at any time, there's a certain proportion of it which is decaying into something smaller. Okay? Constant relative decay rate means exponential decay over time. All right, so that's why collections of radioactive material will exhibit exponential decay. The relative rate of decay is constant, but because it's decaying, it's negative. So the equation will look like y naught equals, or y equals y naught e to the kt, but this time k will be a negative number. Okay, so do I have an example of that? It's actually customary to express the rate of decay in terms of the half-life, the amount of time it takes for a pure sample to decay into a sample which is only 1/2 pure. Okay, so if you've got 100 grams of it, measure the amount of time until you have only 50 grams of pure whatever uranium, and then 50 grams of other stuff, and then that's the half-life. Now, I'll tell you a story. When I was in 5th grade, I was so interested in atomic weapons, I wrote a paper, and I read in the encyclopedias, this is what you had to do before Wikipedia, about atomic weapons, right? And I learned about radioactive decay and all this half-life business, and I thought, that's stupid. Why don't they just double it and say it's the life? So I went through my paper, I corrected all of the half-lives by multiplying by 2 and saying, the life of plutonium is 20,000 years. I still got an A, though. I think I knew more about nuclear weapons than my 5th grade teacher. Okay. So the half-life, let's do an example here. Half-life of polonium-210. Polonium is an element, and the 210 stands for some particular isotope that's really radioactive, is about 138 days. How much of a 100-gram sample remains after T years? Okay. So we didn't tell you a number T. Your answer will involve T, of course. But the important thing is to use that half-life to come up with the function that describes the amount of polonium-210. Okay. Well, to say that the half-life is 138 days means that if you had, say, a 100-gram sample, then after 138 days, you're going to have 50 grams of it. Okay, so if you plug that into the exponential decay rule, y0 equals e to the kt, I'm putting t in years by dividing it by 365 because the question asks for the answer in years. Right? or a function where the input is measured in years. Okay, so 50 is 100 e to the k times 138 divided by 365. That's an equation for k. Divide everything by 100, you get 1/2 equals e to the k times 138 over 65. Take the natural log, and you get that k is negative 365 times the natural log of 2 divided by 138. What it is when you take the natural log of 1/2, it's the negative of the natural log of 2, because 2 to the negative 1 is 1/2. Okay, so you solve the equation, and this is what you get for k. And then you just want to plug that into the function's equation in terms of t, 100 e to the k times t. And a nice way to write that is 2 to the minus 365t divided by 138. Okay, why is that nicer? It's like saying 1/2 to the power of the number of half-lives that have elapsed. So after one half-life, your original sample will be half as much. After 2 half-lives, your original sample will not be completely gone, as it was in my 5th grade paper, but 1/4 of it will be left. After 3 half-lives, 1/8 of it will be left, and so on. Okay. So you've probably been following the news. They've been talking about the reactor in Japan, which got hit by the tsunami, and there's all this radiation and danger of more radiation that's escaping. Recently, they downgraded their estimates of how much radiation had escaped, and it's because that they weren't sure what elements were in the radioactive material that was coming out. It turned out that what was coming out had a much smaller half-life than what they thought was going to be coming out. And since it had a smaller half-life, it decayed faster. And they said, oh, it's actually not as bad as we thought. Still pretty bad, but because they guessed the wrong element coming out of the reactor, then the estimates were a little bit over dramatic. Okay? So that is the deal with radioactive decay of large elements. But small elements can also exhibit radioactive decay. Let's talk about carbon-14. So we're all made of carbon, right? And we're all walking around here, and we absorb cosmic radiation. And the cosmic radiation will, every once in a while, add neutrons to the carbon in our bodies, which is normally carbon-12, and converted to carbon-14. All right, so any given time, any of our carbon atoms in our bodies could be suddenly enhanced to carbon-14. Carbon-14 is radioactive, and it will decay back to regular old carbon-12. Okay? So constantly we're absorbing neutrons, which is converting our carbon into carbon-14, and then decaying back to carbon-12. So back and forth, back and forth, back and forth, until we die, and then we go under the ground. Once we're under the ground, we're not absorbing cosmic radiation anymore. The ground is shielding us from this cosmic radiation. And so we don't acquire any more carbon-14 once we're dead and under the ground. That means that the amount of carbon-14 you have in your body when you die is the most carbon-14 you're ever going to have from then on. And from then on, that carbon-14 will decay exponentially. So if I'm digging something up out of the ground, I can measure how much carbon-14 is left in that thing, whether it's a piece of pottery or a dead body or something, or a mastodon. Then I can work backwards to figure out how long ago it went under the ground. And this is how we find the age of things using radiocarbon dating. Okay. Turns out that the half-life of carbon-14 is about 5,700 years, relatively long, at least for living things that we can recover organic material from. And so you get an equation for the amount of carbon-14 left in something. It's the original amount of carbon-14, or the amount of carbon-14 at the time of death, times e to the minus natural log of 2 divided by 5,700, or 2 to the minus t over 5,700. Okay, so find the ratio of carbon-14 to regular carbon in the body, and then use that to find out what t is, to work backwards and find out when it went into the ground. Okay, so that's carbon-14. Let's do a little example there. Suppose a fossil is found, and in that fossil we find the ratio of carbon-14 to carbon-12 is 10% what it would be if that fossil were a living thing today. So how long ago did it go into the ground? The ratio of carbon-14 to carbon-12 is 10% what it was when it was alive. So we're looking for the value of t for which p of t divided by p0 is 0.1. Okay, I don't know what p of 0 was, but I know that it's 10% now of what it was before. So from the equation, we've got 2 to the minus t over 5700 equals 0.1, and we just need to solve this for t. Okay, so how do I solve this for t? You don't have to tell me the solution. Tell me what you would do to get the solution. Take the natural log, right? The natural log of the left-hand side would be equal to the natural log of the right-hand side. That would pop out this exponent, convert it to a multiple of the natural log of 2. So negative t over 5700 would be equal to the natural times natural log of 2 would be equal to the natural log of 1/10. Okay, so if you do that, what you get is t is the natural log of 1/10 divided by the natural log of 2. Remember that this is not the same thing as the natural log of 0.1 divided by 2. The natural log of a difference, the natural log of a quotient is the difference of the natural logs, but the quotient of natural logs doesn't have a rule to simplify. Okay, so you just had to plug that in, and you would get that t is 18,940 something. So by measuring the ratio of carbon-14 to carbon-12, you can determine that this fossil is almost 19,000 years old. Okay, so we've found fossils which are much, much older than that, and I think that they have to use other techniques besides radiocarbon dating. But this is a pretty useful technique. Any questions about how that works? All right, now you're all equipped to be anthropologists, right? Okay. So what else can we use this constant relative growth rate law, or this exponential equation, for? Let's look at something called Newton's law of cooling. So here we have a delicious cup of coffee, right? And it's giving off heat, as you can see by the steam here. One of Newton's contributions was his understanding of heat and the way heat flows. If you have that cup of coffee and it's very hot, then pretty rapidly it starts to cool down. You've all noticed this if you drunk coffee, right? Tea also works too. If you don't drink coffee, think about tea. If the coffee or the tea or whatever is at room temperature, does it get colder? No, it doesn't get any colder once it hits room temperature. Because heat is motion and things tend to stabilize, and a cup of coffee at room temperature isn't going to get any colder than room temperature just by sitting there. Okay, so if it's very far away from room temperature, then it will cool rapidly towards room temperature. If it is very close to room temperature, the temperature won't change that much at all. And it works the reverse if you pulled some iced tea or iced coffee out of the refrigerator, right? At first it would be cold, but it would start to warm up until it got to room temperature. Okay, so Newton's law of cooling says that the rate of cooling of an object is proportional to the difference between the temperature of the object and the temperature of its surroundings. So if there's a large difference in temperature, the object is very hot, and the surroundings is not so hot, then that object or that cup of coffee will start to cool down. Or vice versa, if it's very cold and the ambient temperature is warm, it will start to warm up. But if they're close, then the change is not going to be that much. Now, like many laws, this is a simplification of what really happens, because as that coffee is cooling down, it's actually warming up the room as well. That energy has to go someplace, and it goes into warming up the room. But if you allow that effect, if you want to measure that effect, you have to use a different kind of equation, which has a much more complicated solution. That's the heat equation. But we often make assumptions which allow us to solve equations simpler, and that's one assumption we'll make. We'll say the amount that the coffee warms up the room is not anything that we can measure. So we'll just say that it cools down. Now, what that means mathematically is that the change in the temperature of the object that's cooling is proportional, that is a constant multiple, of the difference between the temperature of the object and the temperature of the surroundings. Right? That's what I said in words, and this is how we would write it in mathematical symbols. The derivative of the temperature function is a constant times the difference between the temperature function and a constant temperature of the surroundings. Okay? And again, that constant, that k, is going to be a negative number because If the difference is positive between the object and the surroundings, then the change is going to be negative. It's going to be pulled down. If the difference is negative between the object and the surroundings, then the thing will warm up, right? Its temperature will increase. Okay, so once again, a law becomes an equation. This is why differential equations are so useful, is that they're a mathematical expression of the laws of nature. Okay, but how do we solve an equation like that? Well, we had been comfortable with solving equations where the derivative of a function over time was equal to a constant times that function. Those all had exponential solutions. But it's not, we haven't yet solved equations where the derivative is a constant multiple of the temperature or the function minus another constant. So how does that minus constant change the solution? Okay, well, here's a nice trick. This is not the kind of trick which I would have expected you to invent right after looking at this equation. But once you see the solution, you'll see how useful it is. What we'll do is change the variable, change the unknown function from the temperature to the difference between the temperature and the surroundings. So instead of looking at T of T, we'll look at T of T minus T sub s. And we'll call that equation Y of T. Now, the equation for T of T can be rewritten to give us an equation for Y of T. T of T has this equation that dt dt equals constant times T minus T sub s. This is Y. And dt dt is the same as dy dt because y and t are different by a constant. So the fact that t satisfies this differential equation on the left tells you that y satisfies the differential equation on the right, dy dt equals k times y. And that's the equation I know how to solve. Y then has exponential decay, constant times e to the kt, which is useful, right? But it's not so useful because I wanted to know what t was, but that's fine. I can just substitute back in t. T minus surrounding temperature is equal to constant times e to the k times time. And so you can write the temperature function as c e to the k times time plus surrounding temperature. And what is the c? The c is y sub 0. That is the difference between the temperature and surrounding temperature at time 0. So the equation that you get is that T of T is C minus T sub s, or T0 minus T sub s, initial temperature of the object, constant temperature of the surroundings, e to the kt plus s. Okay, so that's complicated. You don't have to memorize the thing in the box. As long as you understand the procedure, you can reproduce it and come up with this equation later on. Now, but let's take a look at it just to make sure it makes sense. K is going to be negative. So what's the limit of this function as time goes to infinity? What's the limit of this function as time goes to infinity? The limit is the initial temperature, because this part here, well, e to the kt, that's going to go to 0 because k is negative. So this whole multiple of e to the kt, that's all going to get erased. And so the only thing left is this constant T sub s. And that reproduces what we would expect. The cup of coffee, when it cools, it approaches the room temperature. It doesn't continue to cool down to absolute 0. Once it reaches room temperature, it stays there. Okay? So that's Newton's law of cooling. So let's forget about coffee and make some eggs. Hard-boiled egg at 98 degrees Celsius. 98 degrees was the boy band in the 90s. You guys remember that? Carly remembers that. Nick Lachey was in 98 degrees. That's how he became famous. Okay, 98 degrees Celsius is egg is put in a sink of 18 degrees Celsius water. If you're not so, if you don't have your metric benchmarks, then room temperature is about 20 degrees Celsius, and body temperature is about, I think, 27 degrees Celsius. 37. Yeah, 37. I don't even. I'm married to a Canadian. I don't know my Celsius that well. Okay, and 100 degrees Celsius is boiling. So this egg is almost at boiling temperature for water. It's put into a sink of water which is less than room temperature. And then after 5 minutes, the egg's temperature cools to something a little bit more than body temperature. Now, assuming the water has not warmed appreciably, how much longer will it take the egg to reach 20 degrees Celsius? So this part here about assuming the water has not warmed appreciably, that's code for letting you know you can use Newton's law of cooling. Okay? If you need to measure the rate at which the water warms up, then we can't use this rule that we just derived, but we're allowed to. So that's okay as long as it's a big enough sink. Okay. So how much longer will it take the egg to cool to 20 degrees Celsius? So what's the equation? The equation is temperature at time t is the initial temperature minus the surrounding temperature, e to the kt, plus the surrounding temperature. Now what's the surrounding temperature? It's 18 degrees. What's the initial temperature? It's 98 degrees. So the initial difference between object's temperature and surrounding temperature is 80 degrees. Temperature at time t is 80 e to the kt plus 18. What is it we wanted to know? We want to know the value of t for which t of t is 20 degrees. The value of t for which t of t is 20 degrees. But I also don't know k. It looks like I'm going to need to find k. Okay, so the equation I have is 80 e to the kt plus 18. If I plug in t equals 5, what is the temperature? Test of eyesight, right? If I plug in t equals 5, what is t of t? 38 degrees, okay? And so the equation I'll get is 38 equals 80 e to the 5k plus 18. Subtract the 18 from both sides. 20 equals 80 e to the 5k. Need to solve this for k. So let me divide everything by 80. 20 divided by 80 is a fourth. And the other side is e to the 5k. Nothing I can do now except take the natural log. So let's do that. Natural log of 1/4 is 5k. And solve this for k. K is 1/5 times the negative of the natural log of 4. Do you understand why the log of 1/4 is equal to the negative natural log of 4? Because 1/4 is 4 to the minus 1. Okay? I like to write natural logs this way because this reminds me that it is a negative number. Otherwise, I have to remember that if the natural log of something less than 1 is negative, but if I have a negative out there, it reminds me that it's negative the natural log of 4. Negative something that's positive. Okay, so that's good. I've got k now. That wasn't the thing I wanted, though. I wanted to find a certain t. I wanted to find the t for which 20 equals 80 times e to the minus t over 5 natural log of 4 plus 18. So how do I solve that for t? Well, again, the unknown thing is in the exponent. So I'm going to eventually have to take a natural log. Here's my equation. Is that too fast? Is anything? Sorry, I'm going backwards. Okay. This is the equation that I have to solve for t. What would be the program? Take the 18 and subtract it from both sides. Then divide by the 80. Then take the natural log. Okay, wave at me frantically if you do not want me to go on to the next slide. I'm not. Should it still be 38 on the other side? Let's go back to the problem. Okay, we're looking for when the temperature is 20. Okay, so we do want the 20. We want the value of t for which t of t is equal to 20. Okay, so let's go ahead and solve that. 20 equals 80 e to the minus t over 5 natural log of 4 plus 18. Subtract the 18, we'll get 2 equals 80 e to the minus t over 5 natural log of 4. Divide by 80, and we'll get 1/40 equals e to the minus t over 5 times the natural log of 4. Take the natural log, we'll have negative natural log of 40 equals negative t over 5 natural log of 4. And so t is the natural log of 40 divided by 1/5 natural log of 4. Okay, anytime you've got a fraction where the denominator has a fraction, you can multiply by the reciprocal, and you get 5 times the natural log of 40 divided by the natural log of 4. No cancellation here, right? Because we have no rule for the quotient of two logarithms. We just have to plug it in, and if you plug it in, you'll get something around 13 minutes. Okay, so that's how long you should wait until you take your egg out of the water. So you can make similar experiments for finding out how long to keep an egg in the hot water. How many like to eat hard-boiled eggs? Okay, now you know if you leave that egg in the boiling water too long, then the yolk gets all hard and it gets this green film on the outside, and it's no good anymore, right? So you want to find the sweet spot where the yolk is not runny, but it isn't overcooked. You can use Newton's law of cooling for that, if you like that kind of thing. Okay. Usually I do this around Easter time, too. It becomes even more relevant. Any questions about this one? Okay. Let's spice it up then and talk about murder. A murder victim is discovered at midnight, and the temperature of the body is recorded at 31 degrees. 1 hour later, the temperature of the body is 29 degrees. Assume that the surrounding air temperature remains constant at 21 degrees. Calculate the victim's time of death. Now this is getting interesting. Okay, you arrive on the scene of the crime. You don't know when this body was most recently living. So you measure the temperature as soon as you get there. Wait an hour and measure the temperature again. Work your way backwards to figure out when that temperature was living body temperature. Okay. So what do we have? We know the temperature when we get there. It's 29 degrees. We know the temperature 1 hour later. It's 21 degrees. And we want to know the time that the temperature was 37 degrees. Right? We know that the room temperature is 21 degrees, and we're clued in that the room temperature is constant, so we can use Newton's law of cooling. All right, so what equation do we have? Our equation is the same temperature equation. Initial temperature is 31 degrees. The surrounding temperature is 21 degrees. And temperature at time 1 is 29 degrees. Now, when I say initial temperature, I don't mean the initial temperature of the person. I mean the temperature when I got there, right, at the moment the experiment started. I want to know how long ago the temperature was 37. So let's solve that equation. Well, 29 is the temperature at time 1 hour. So 29 is 10 times e to the k times 1 plus 21. What is the 10 here? That's the difference between the initial temperature, T0, and the surrounding temperature, T sub s. I think my pointer is losing its steam here. The initial temperature is 31. The surrounding temperature is 21. So the initial difference is 10. That's why we have a 10 in front of the exponential term. Add to that the surrounding temperature, 21. And that's the equation that we get. So how do you solve this? Well, you solve it the same way we've been solving these equations with unknowns in the exponential. You subtract the constant to get 8 equals e to the k times 1, or 10 times e to the k times 1. Divide by 10, and then take the natural log, and you get that k is equal to the natural log of 0.8. Okay? If this is hazy for you, put a little star by it. Then later on, when you go back through your notes, see if you can solve this equation and get this answer here. Okay. To find t, plug it back into the equation. What we want to know is the time for which the temperature is 37. That's the temperature of a living body. So fill in the equation, unknown thing, time, and solve for time. 37 minus 21 is 16. Divided by 10 is 1.6. Take the natural log and divide by the natural log of 0.8. You get natural log of 1.6 divided by the natural log of 0.8, and that's negative 2.10 hours. Should it be negative? Yes, because we measured its rate of cooling, and we want to know when it was a higher temperature. So that should be, some time ago. Okay, so the time of death was just before 10 p.m. A tenth of an hour is 6 minutes, so 9:54 p.m. the body was last alive. Pretty interesting? Now, that's only one technique to find the temperature of the body. Oftentimes, they have a body which has been dead for much longer than that, and Newton's law of cooling is not going to work because it's already cooled to room temperature. Do you guys know of other scientific techniques to measure time of death? You guys haven't eaten lunch yet, right? Entomology, that's right. You count the number of bugs that are living in the body, and bugs like, will reproduce exponentially. So you can work backwards and figure out when those bugs started infesting that body. That's how they found out the time of death for Lacey Peterson when she washed up on the shore. They counted the bugs. Okay. Other questions about CSI or other uses of Newton's law of cooling? Okay. So one final example of exponential growth is something that we touched on when we first learned about the exponential function, the idea of continuously compounded interest. Now, what we said was that if you have an account that earns interest and that interest is compounded, then the growth is going to satisfy some power law. And the more often you compound it, the quicker your balance will grow. But there's a limit to how often you can compound it, and then there's a limit to the rate at which your balance grows. Okay? So we did this before in generality. If you have compounded interest rate r times per year, r% each year, compounded n times, then an initial deposit of A0 gives a balance of A0 times 1 plus r over n to the nt. If you let the number of compoundings go to infinity, you get A naught e to the RT. Okay, and this is a much simpler function to deal with in a calculus way than this function here. And so a lot of times if we're doing an analysis, we'll substitute continuously compounded interest for discretely compounded interest. Even though in the real world we don't get continuously compounded interest, it just makes our lives a little bit simpler to assume that we have continuously compounded interest. Now, is that a reasonable assumption? Let's do an example where we compare continuous compounding and discrete compounding. Okay? Yes, dollars are like bacteria. They grow and grow and grow. Maybe at a very small rate, but they do grow. So say we got two bank accounts. One has 10% annual interest compounded quarterly, and another one has continuously compounded interest, but we don't know the interest rate. What is the interest rate, R, if they have the same balance after every year? Okay? So 10% compounded annually is equivalent to what compounded continuously? Let's see if we can solve that equation. If the, well, I said quarterly, huh? 10% annual interest compounded quarterly. Okay. So if one bank account has quarterly compounded interest, then after t years, you have your initial balance A0, which I for some reason renamed to P, times 1.025 to the fourth power to the t power. This is 1 plus 2.5% compounded 4 times each year. On the other hand, the second bank account has a balance which grows exponentially. Its equation is going to be the initial balance A0 e to the RT. So for which R is 1.025 to the 4t equal to e to the RT? That's the equation we want to solve. For which R is 1.025 equals to the 4t equal to e to the RT. Okay, well, if you just divide one by the other, if these are supposed to be the same, these are definitely the same. What you'll get is that 1.025 to the fourth power has to be e to the r. And so r is natural log of 1.025 to the fourth power. That is 4 times the natural log of 1.025, which is about 0.0988. Okay? So because we have a solution, we can say that 10% annual interest compounded quarterly is equivalent to 9.88% interest compounded continuously. So if you're doing some kind of analysis about interest over time, you get to assume that interest is compounded continuously just by adjusting the interest rate by a small amount. All right? There's no loss of generality in assuming that interest is compounded continuously, even though it's not. And what happens a lot is that you'll have interest rate which is compounded, say, quarterly, and you'd like to know what the effective annual interest rate is. And if you look at your credit card balances or your 401k, you guys have 401ks, right? They will give you an effective annual interest rate. Okay? And they're solving an equation like this. All right, one more of these. How long does it take an initial deposit of $100 compounded continuously to double? Okay, I didn't give you the interest rate. Obviously, the answer is going to depend on what the interest rate is. But what we're given is that the initial balance is 100, and we want to know for what t, what time value, will we get 200. Well, that's the equation that we want to solve. 200 is equal to 100 e to the rt. Divide out that initial balance, and we'll have 2 equals e to the rt. Solve for t. You get that t is equal to the natural log of 2 divided by r. Notice that this time value, the doubling time, doesn't depend on your initial balance because the growth rate is proportional to the amount you have. If you put in $100, it's going to take this much time to get to 200. If you put in $1,000, it's going to take this much time to get to 2,000. Okay? It's just a doubling law. So for instance, if you've got 6% interest, yeah, in my dreams, then the doubling time will be 0.69 divided by 0.06. 69 divided by 6 is about 11.5 years. Okay. If you have 1% interest, and my bank account has almost 1% interest, then it looks like it'll take 69 divided by 1, about 69 years to double the amount of money in my savings account. I don't have that much in there anyway, so 70 years before I get another dollar of interest. Okay, so that's the doubling time. And it depends on the interest rate. It does not depend on the initial balance because you're only measuring the doubling time. Now, if you want to find out how much time it takes to get to a certain value, well then, yeah, that is going to depend on how much you put in there. So if you're trying to make sure you have $2 million by the time you retire, well then, yeah, that's going to depend on how much you actually save. But if all you're measuring is how fast you double, then that doesn't depend on how much you have. Now, this rule here, the natural log of 2 divided by the interest rate, natural log of 2 we said is 0.69 something, right? Round it up to 70. You can even round it up to 72 if you want. And you get something called the rule of 70, or alternatively, the rule of 72. If you want to find the doubling time, take 70 or 72 and divide it by the interest rate. Okay? It's an estimate anyway, so if you want to estimate, you can use whichever one has the nice factor. The interest rate's 5%. 70 divided by 5 is 14. You would expect about 14 years to double. If the interest rate is 6%, 72 divided by 6 is 12. So about 12 years to double. Okay? That's in case you want to become an investment banker, you can use that handy back-of-the-envelope calculation to find doubling time. Okay. So those are many of the applications of exponential growth and decay. We see they're all over the place. Anytime you have an equation with an unknown and an exponent, you can solve that using logarithms. And remember that your friend list is a culture of bacteria. Haha. Okay, that's it. You have 10 extra minutes to frolic with your friend.